Firstly, before we go any further, please pause the video here and read this notice. This video is intended to give you an overview of how to build a valve or tube guitar amp, as our American cousins say, and looks at what results you can get once it's done. The build follows the guidance of Dave Hunter on how to build his two-stroke amp in his book, the Guitar Amp Handbook. The video is divided up into convenient sections. Firstly, with so many amps available to buy, why build one? Apart from the fact it's a lot of fun, the two-stroke has some really attractive features to warrant all the effort. Over the next few sections we really get into the weeds over the details of the amp and how to make one. But if you're just interested in what it sounds like, skip ahead to the demos at the end where it's used with various guitars. But if you'd like to accompany me into the weeds, let's dive into the details. How did the two-stroke come about, and why is it based on the 5F2A Tweed Princeton of 1957? The beauty of the two-stroke is that it's a platform that allows you to develop it in directions that suit you. You can see here what I did. How do you actually build a valve amp? You can see here how I tackled it, as well as the mistakes I made along the way. It is vital to undertake structured testing under safe conditions. You can see here how testing uncovered mistakes made in construction. When all is said and done, you own an amplifier for what it can do for you. So how does it sound? I tested the amp with the 4 classic solid electric guitars to find out. Lastly, there are some great resources available without which I would not have attempted this project. I give a shout out to them in this section. But why build a valve guitar amp, and why build the two-stroke? Like everyone else, as I have progressed through my guitar playing career, I have bought many guitar amps over the years trying to emulate the guitar tones that I've heard on records and heard at gigs. I have owned and continue to own a number of guitar amps, but by and large they are simply too loud for regular home practice and recording. At one time you only played a small budget amp if you couldn't afford a large amp, never mind the damage to your hearing, and many small budget amps weren't very good. In these enlightened times, manufacturers offer great quality, fully featured small amps for home recording and practice. There are plenty of them out there, not to mention low power modelling amps, and I already own a few, so why build one? Apart from the fact that building a valve amp is a huge amount of fun, the two-stroke has features that make it really appealing to those guitarists who like to experiment with their sound. The two-stroke is a clever design because, unlike most other valve amps, it allows you to use a variety of preamp and power tubes for different tones and degrees of distortion. It can do that because it is cathode or self-biased, and it has been specially modified. A number of amps like the two-stroke will let you use different preamp tubes, but few will let you use different power tubes as well. As an example, I would like to try out a KT66 power tube, but the classic KT66 powered valve amp is the Marshall JTM45, which is very expensive and massively loud. However, you can use a KT66 in a two-stroke, which is a low power single-ended amp. The two-stroke can use a KT66 for just 9 watts of output power. Furthermore, unusually and desirably, the two-stroke has a valve rectifier, while most small valve amps today have a silicon rectifier. This is part of the mojo of a vintage valve amp's sound. Valve or tube rectifiers aren't popular with amp manufacturers because they're expensive. They require a separate 5-volt power supply, and a valve, a socket and wiring are much more costly than a few diodes. The two-stroke normally uses the 5Y3 rectifier, but it can use others like the 5U4. In his book, Dave Hunter says that the two-stroke amp is an extremely tactile, touch-sensitive amp that responds incredibly well to your playing and provides a cranked-up sounding sweet spot at levels that are great for studio recording, the home player and smaller rehearsals. It should be perfectly suited to my current needs. Later we'll put those claims to the test. While the two-stroke was designed to be a very versatile amp, it was never intended for use with some modern genres like metal. So if you're interested in that, you probably need to look elsewhere. The two-stroke amp was conceived as a small combo based on the Tweed Fender Princeton 5F2A amp introduced in 1957, and it is built on a Tweed Princeton chassis and circuit board. It grew out of a project that Dennis Cornell of Cornell Amps designed for the Guitar magazine when Dave Hunter was the editor, the Stinger amp. The Stinger project was featured in the March 2001 edition of the magazine. Dennis developed the Stinger into his Romany amp, and Dave Hunter used what he learned to develop the two-stroke. The project originally started as a dual single-ended amp with two 6v6 output valves operating in tandem as a single-ended amp rather than as a push-pull amp, hence the name two-stroke. However, in the updated version of the book, Dave stated that in his opinion it sounded better with just one 6L6 valve, and so the updated design does away with one of the output valves. The sharp-eyed will spot that the single remaining output or power valve is marked as V4 on the schematic, even though it is one of only 3 valves. I should mention that the official manufacturer of the two-stroke kit is the Victoria Amplifier Company. You can of course put the kit of parts together yourself using the book as a guide, but as you can see from these pictures, if you want to make it easy on yourself, you can order Victoria's kit, which looks really good. Turning to the Tweed Princeton, it is essentially a tweed champ with a tone control. Its key characteristics are valve rectification, so that the amp provides the characteristic voltage sag in output, single-ended operation with one power valve providing all the output. By their nature, single-ended amps are class A in operation, and it has a cathode biased power valve. These features should give a bluesy quality to the tone more typical of a vintage valve amp rather than the crunch of a straight ahead rock amp, and that's the tone that I'm looking for. The Tweed Princeton uses a 5Y3 rectifier tube, a 12AX7 preamp tube and a 6V6 power tube. Some people don't think it's as good as a champ. That's because the inclusion of a tone control leads to some reduction in gain even when the control is dimed, as a result of what is termed insertion loss. Recognising the problem, Fender increased the gain in the preamp tube of the Princeton slightly by adding a 25 microfarad capacitor across the first preamp stage bias resistor found in the champ. However, given that we can use more powerful valves than the 6V6, plus the other modifications, there shouldn't be any noticeable loss in performance from the two-stroke. Although the Tweed Princeton is a great amp, Dave Hunter tweaked the Princeton 5F2A to create the two-stroke in the following significant ways. The two-stroke is specifically designed to make it possible to use a range of power valves. Neither the Tweed Princeton nor indeed the Tweed Champ are capable of running anything other than a 6V6 output valve reliably because their transformers aren't really up to it. The two-stroke design uses beefed up power and output transformers. US power tubes like the 6L6 do not use pin 1 in the octal socket, so Fender regularly uses pin 1 as a terminal. However, the British EL34 and KT66 valves do use pin 1, so the octal socket has to be rewired to accommodate the EL34, the KT66 and the 6L6. The two-stroke uses a switchable bias on the cathode of triode 1 to give different types of gain. It's a clever way of voicing the amp for different types of distortion while avoiding inserting anything in the signal path which might adversely impact tone. In the middle position, the preamp tube is biased by a 1.5K resistor to give a blackface type tone. Flicking the switch down adds a 25 microfarad capacitor in parallel with the resistor to give a more plexi-like tone. Flicking the switch up swaps a 25 microfarad capacitor for a 0.47 microfarad capacitor for a more traditional tweed tone. The Tweed Princeton has an output impedance of 4 ohms, but the output transformer for the two-stroke can provide an output impedance of 4 or 8 ohms. The primary impedance required by a standard 6V6 valve is double that of the 6L6 and EL34. To make the amp as flexible as possible, the output transformer can output into an 8 ohm load with larger power valves. However, with the 6V6 you plug an 8 ohm speaker into the 4 ohm socket to give it a better impedance match. The Tweed Princeton uses a single heater filament supply, and the return is via the chassis, which can lead to more hum. However, the two-stroke uses a twisted pair heater circuit as per later and bigger Fender amps, avoiding the return through the chassis to minimise hum. There are various other more minor tweaks to give the two-stroke its unique design. While the two-stroke satisfied many of my requirements, I wanted to make some modifications of my own. I built a Fender Princeton Reverb clone from a Mojo Tone kit about 10 years ago, So I've had experience of making valve amps before, and so I knew what some of the challenges could be. In that project I got terrible motorboating. This means that the amp produces a loud put-putting sound. This was due to poor wiring layout and it took some time to correct. In this build therefore, if I was going to deviate from the standard two-stroke design, I was determined to avoid this problem, and a great deal of thought was therefore given to layout and lead dress. Firstly, to give more space to work and to add some tweaks, I decided to go with a JTM 45 style and sized aluminium chassis. Since it's a better electrical conductor than steel, aluminium has the benefit of a faster electrical response, and the larger size has the benefit of providing more physical separation for the preamp and power sections for lower inherent noise. Secondly, I just wanted a head that I could use with various speaker cabinets rather than the full combo. I decided to build a Marshall style cabinet to accommodate the chassis. Because of the physical size of the KT66 output valve in particular, it resulted in a relatively tall cabinet. I wasn't that bothered about making a super compact amp, so it wasn't a problem for me. Dave Hunter had gone with the standard Fender switch logic, from left to right, tone control, volume control and boost switch. As a Strat and SG player, I am more used to moving from left to right, pickup selector switch, a volume knob and a tone knob. This required a redesign of the circuit board and risked greater noise, but in the end the results justified the effort. Please note that my version of the two-stroke goes to 11 on both the volume and the tone controls. In his book, Dave Hunter used an on-off-on boost switch with its default centre position being the blackface tone. He then switched down for the plexi tone or up for the tweed tone. I wanted to have progressively greater distortion, which had from top to bottom blackface, tweed, plexi. This necessitated an on-on-on switch, which proved a little more difficult to source than the standard switch at an acceptable price. My output transformer came with a 16 ohm tap, so I added a 16 ohm output. For safety's sake, I added a bleed resistor across the first reservoir capacitor to drain off electricity when the amp is turned off. For added versatility, I also wanted to provide for switchable rectification from the standard valve rectification to silicon diode rectification together with the sag resistor. The sag resistor is supposed to simulate a valve rectifier, and I wanted to see how true that is. I wanted to add variable negative feedback. The more powerful Tweed Deluxe amp does not have negative feedback, but the Tweed Princeton on which the two-stroke is based does. I wanted to be able to experiment to see whether there was any meaningful difference in tone. The results of these experiments will be the subject of a future video. Lastly, a major realisation was that the valve amp circuit board should really be called the valve amp circuit board, as it accommodates several individual independent circuits performing different functions. Therefore, the board needs to be designed so that the function of, say, removing alternating current ripple from the power supply does not interfere with, say, the audio signal entering the preamp and power tubes. The various circuits on the board are smoothing capacitors, power valve bias, preamp valve bias, valve signal path and audio input. I use perf board of the size used in the JTM 45. Which is physically bigger than the Tweed Princeton board used in the two-stroke. This meant that the circuit wasn't too cramped and I could add extra components like the bleed resistor, sag resistor and silicon diodes. When it comes to actually building the amp, the place to start is to lay out the chassis and drill the various holes needed. I'd intended to use hole punches to make holes for the valve bases, but found the sheer physical effort required for an octal base was beyond me. I therefore used cone cutters, having marked out and drilled pilot holes in the right places. If you're not using a pre-punched chassis, one thing to note here is to mount the various switches and jacks in the front and rear faces before deciding where to put the circuit board and transformers. I didn't and discovered that one switch fouled the circuit board, hence I had to reposition the board. In laying out the chassis to your own design, you need to think about neat cable runs, no wires crossing and the positioning of earth or ground points. A good principle in assembling an amp is keeping it as light as possible for as long as possible. So add the tube sockets, jack sockets, pots, switches, earth points and indicator lamps before adding the circuit board and transformers. After loading up the hardware to the chassis, the next task was to assemble the circuit board. The The JTM45 circuit board uses turret board construction. In this form of construction, tin-plated brass turrets are pressed and secured by swaging the turrets into a sheet of non-conductive material like phenolic using a punch and an anvil. You can either use a phenolic board, which you can drill for turrets in the correct places, or use a pre-drilled board. I chose to do the latter as it was just easier for a prototype board. You then populate the board using pliers to bend the component leads before soldering the components in place. It's a good idea to add flying leads to the circuit board, which can then be trimmed to length and soldered to the chassis components once the circuit board is fastened in place. Having checked and double checked the circuit diagram, the circuit board was mounted in the chassis and wired up to the switches, jacks, transformers and valve sockets. Firstly, I will repeat the warning given at the start of the video here. If, at your own risk, you are going to undertake your own testing, then you should aim for best practice, which includes these items here. I am very grateful to Barry at Ampmaker for his test process, which I have adapted. Firstly, test all ground connections by plugging a kettle lead into the IEC socket and checking the continuity between the earth pin of the plug and the earths in the amp, the earths on the guitar lead and on the speaker lead. This threw up a major fault. The most important single connection in any mains electricity powered amp is the safety earth bond. This runs from the earth terminal of the IEC socket to a chassis bolt. I had used a crimp ring terminal, and though it looked sound, it turned out that it wasn't. To crimp the terminal onto the cable, I had used a pair of pliers. The purchase and use of the proper crimping tool for the job remedied the fault, and I could continue testing the amp. All other earth connections were crimped with the correct tool and retested. It is recommended that some form of current limiting device is used the first time the amp is powered up. The most expensive components in an amp by far are the power and output transformers, and they need to be protected from any mistakes or poor soldering. One solution is a Variac, which is quite an expensive variable voltage controller. However, for less than £20 I built a dim bulb tester. This places a 100 watt incandescent light bulb in series with the power supply. If the bulb shines brightly, there is a short in the amp and it should be switched off immediately. If the bulb shines dimly, then it is functioning as it should. The ripple capacitors also benefit from having limited current applied in the first instance. I was fortunate and the dim bulb tester showed no faults. The next step is to connect the amp to the mains electricity supply, having inserted a load into an output socket before turning the amp on. It is vital that the output transformer sees load, otherwise it could burn up. I built a simple switchable 4 or 8 ohm load using 25 watt resistors. You can also use a loudspeaker, but when you're undertaking voltage tests you will experience loud popping sounds. Unplug immediately if there is any smoke coming from any component. I then check the voltages in the amp using the safety protocols outlined at the start of this video and the recommended voltages for the amp. All voltages checked out, the amp was very quiet and produced very little noise, which was a relief after the experience with the Princeton Reverb clone. However, the low output wasn't right and it was time to check through the circuit again. The two-stroke uses negative feedback from a tap off the output transformer secondary back to the input of the preamp valve. I hadn't been provided with a drawing of the wires from the output transformer and, naively, hadn't realised that the different outputs were taps, not separate circuits. I had bridged the 3 output sockets for the negative feedback circuit, not realising that this means that the amp would always be giving an output impedance of 16 ohms. The 8 and 16 ohm bridges were removed and all of a sudden, into an 8 ohm speaker, the volume went up dramatically. It is worth remembering that any negative feedback circuit should always be attached to the lowest impedance tap in a multi-output impedance amp, which will always be in the circuit even if higher impedance sockets are used. With a single-ended amp with an AC heater supply, it is unlikely that the amp would be completely hum-free. However, the hum situation with the amp is as follows: no input, no hum at all, guitar plugged into the input and the volume control turned right down, a very modest hum, guitar plugged into the input and the volume control dimed, marginally more hum. So we have a working amp that is low noise, which is great, but the crucial issue is, what does it actually sound like? I wanted to put the amp through its paces with the 4 main types of solid electric guitar, so I tested it with a humbucker equipped Les Paul guitar, a P90 equipped SG guitar, a Telecaster and a single coil equipped Stratocaster. The number of variations in tone and pickup combinations is huge, so for testing purposes I decided to concentrate on core applications rather than tones, so clean rhythm guitar, crunchy power chords, overdriven lead tones. Rather than try and dazzle you with my technique, I thought it was better to use a simple, slow piece of music to demonstrate the amp. The amp can take at least 3 different rectifier valves, 3 different preamp valves and 7 different power valves, which would give 63 combinations. For the video I used the standard 5Y3 rectifier valve, the standard 12AX7 preamp valve and a 6K6 power valve. The 6K6 gives just 3 watts of output power, but in a recording situation I found that to be plenty. The boost switch was set to the middle position, the tweed setting, and left for all the tests. The amp was plugged into a Celestian greenback 12-inch speaker in a closed-back cabinet. The microphone used was a Marantz ribbon microphone. Here is a demonstration of the amp used with 4 different guitars. No effects or post-production has been used on any of the guitars. Just to test out what the amp might sound like in a band situation, I put together a short track to show off the various parts in the context of a complete track. Apart from reverb and high-pass filtering, where everything below 100 Hz was cut, no effects were used on the guitar tracks. The wah and pad were not recorded using the two-stroke. So how did the amp match up to Dave Hunter's claims? I like the clean tones, which are round and warm. There is plenty of range in the tone control, and to my taste it was better to cut the treble, as you can see from the position of the tone knob on the right. It was left in this position for all the tests. For the power chords I increased the volume a little just to the edge of breakup. For the solos I increased the gain a little. I never felt that the amp couldn't give me what I wanted, and remember that no pedals or effects were used. Overall, I'm delighted with the amp and look forward to experimenting with different valve combinations. As well as using Dave Hunter's book, I wouldn't have had the confidence to undertake this project without the contribution of a number of individuals. Michael at Modulus Amplification provided many of the components and produced the superb logo plates and front plate. Barry at Amp Maker provides a wealth of construction and test information on his website. I have bought his N5X kit, and that will be the subject of a future video. Merlin Blenko is the valve wizard, and he provides a wealth of information about valve amps on his website. I bought his book, Designing Tube Preamps for Guitar and Bass. Gerald Webber is the founder of Kendrick Amps. I've read 2 of his books which I highly recommend. Tube Amp Talk for the Guitarist and Tech, and a desktop reference of hip vintage guitar amps. I also own one of his Kendrick Model 118 amps, which is a tribute to the Fender Tweed champ of the 1950s. Rob Robinette has an excellent website where he gives masses of advice on how to modify and troubleshoot valve amps. Terry at D-Lab Electronics has produced a fantastic range of tube amp related videos on YouTube, which I have greatly enjoyed viewing. Lastly, I have enjoyed reading Inside Tube Amps by Dan Torres. Don't forget, if you like this video, hit the subscribe button below.